Good morning, students. In the previous lecture, we studied Laplace transform and region of convergence. And especially we studied how region of convergence determines the existence of Laplace transform, the two types of signals, the right-sided and the left-sided signals. As you remember, for example, a right-sided signal having region of convergence starting from the right of the rightmost pole here and to the right and left side signal to the left of the leftmost pole, which is given here, and two-sided signal having a region of convergence, a stripe. And also we saw some of the properties of Laplace transform, such as the linearity property ax1t plus bx2t. The Laplace transform is ax1s plus bx2x, and the time delay property x of t minus capital T e to the power of st times x of s, where the region of convergence of this is the region of convergence of x of s, and the convolution property y of t, which is x of t convolved with h of t, y of s is equal to h of s times x of s. And that means convolution in time domain is multiplication in the Laplace domain, where h of s is equal to y of s over x of s. H of s is called the transfer function of the system. And we saw the derivative property d by dt of x of t is the Laplace transform is s times x of s. And if I have second derivative of x of t with dt is s squared x of s, and so on. And the integration property, the integration of x of tau d tau from minus infinity to t is 1 over s x of s, and so on. Okay, now in today's topic we will see analysis and characterization of linear time invariant system using Laplace transform. Especially we will see the properties of causality and stability. Okay, as we said earlier, if I have a system h of t here, I have input x of t, y of t is x of t convolved with h of t, y of s is x of s times h of s. H of s is y of s over x of s, which is called the transfer function of the system. H of s, if the region of h of s includes the imaginary axis, that means the j omega axis, then h of s will become stable, and also the h of s, the value of h of s at s is equal to j omega is called the frequency response of the system. The frequency response of the system. So what is causality of a system? In chapter 1, we defined causality as a causal system is a system where the output at time t depends on the past or the present, or both the past and present. That means the value of the output, the value of y at time t depends on the past values of x of t, or both the past values of x of t and the present value of x of t, or only the present value of x of t, but not on the future. And in chapter 2, we studied another alternative definition. A system is causal. An LTI system is causal if h of t is equal to 0 for t less than 0. That means by looking only the impulse response, we can draw the impulse response. And if we see the impulse response as a function of time, and if we see that h of t is equal to 0 for t less than 0, and we say the system is causal. And of course, it is right-sided because of the presence of ut also. The region of convergence associated with the system function for a causal system is a right half plane. It's a right half plane. For example, if we see this example, h of s 1 over s plus 1, real of s is greater than minus 1. which means it starts from -1 and to the right of the rightmost pole. It has only one pole, this one at -1, but some transfer functions may have more than one pole. In that case, the region of convergence should be to the right of the rightmost pole, to the right of the rightmost pole. So for this system, for this example, for example, h of t e to the power of minus t ut, then this system is causal. The region of convergence is associated with the rational system function. If I have a certain transfer function, then it is causal. If the region of convergence is in the right half plane and to the right of the rightmost pole. Let's have this second example. Is this system causal? We can check this by looking its poles and also by going to time domain. If we see the region of convergence here is real of s greater than -1. So sure, this is the right side signal because real of s is greater than -1. But I have e to the power of s. So there is a time delay. Time delay, if I go back to the time delay property, what is that the amount of time delay? The amount of time delay, because it is e to the power of s, t, capital T is -1. So when capital T is -1, this will be e to the power of s, and this will be x of t plus 1. So x of t plus 1 means shifted to the left by 1. So let's go to the system. So this system, originally without e to the power of s, I have e to the power of minus t ut. But because I have e to the power of s, time delay, then this will be e to the power of minus t plus 1 times ut plus 1. So what is h of s? H of s is e to the power of s over s plus 1, real of s greater than -1. However, if we see this system, is this causal or not causal? No, it is not causal. Why? Because there is a value between -1 and 0. As you see from this time domain expression, this signal for t less than -1, it is 0, but for t greater than -1, it has some value, exponentially decaying, of course. Therefore, this system is non-causal because it has value between -1 and 0. Therefore, causality implies that the region of convergence is the right of the rightmost pole. If a system is causal, we know that its region of convergence is to the right of the rightmost pole. But the converse is not true, which means a system which is having a region of convergence to the right of the rightmost pole is not necessarily causal. Okay, this is what it means. So if I, for example, if I see this system, its region of convergence is to the right of the rightmost pole, which is greater than -1, but it is not causal. So a causal system has its region of convergence to the right of the rightmost pole, but a system with a region of convergence to the right of the rightmost pole is not necessarily a causal system. Okay, let's study stability. What is a stable system? In chapter 1, we defined a stable system is a system whenever the input is bounded. That means the absolute value of the x of t is less than some value, then the output y of t should be less than a certain value for all time t. Okay, it should be noted that this should be true for all time t. If the input is bounded, if the absolute value of x of t is less than a certain value, then the output y of t is less than a certain value for all time t. This is the definition of stability in chapter 1. In chapter 2, we studied an alternative definition. So a system is stable if its impulse response is absolutely integrable. That means from minus infinity to infinity, the integration of h of t, the absolute value of h of t dt is less than infinity, or the energy of the signal, the impulse response is finite. Okay. Or here in the Laplace transform case, if the region of convergence of the system includes the j omega axis, then we say the system is stable because its Fourier transform exists. Now let's analyze this system h of s minus 1 over s plus 1 times s minus 2. It has several alternatives depending on the region of convergence. So h of t will have three different possibilities. Let's go, for example, let's see the class notes here. Yes, this is, as we said, the right and left sided signal. Let's see this example now. We have this h of s, okay? H of s minus 1, s plus 1 times s minus 2. Find h of t for the three different cases of region of convergence. Okay. Now, here, what are the poles? The poles are s is equal to minus 1 and s is equal to 2. What about the zeros? S is equal to 1 and another 0 at s equal to infinity. So this is the pole 0 diagram plot. So I have a pole at minus 1 here and at 2 here and a 0 here at 1. And the x-axis is real of s, which is equal to sigma. We know this. The x-axis is the real of s. And the y-axis is the j omega axis. So how many possible region of convergence we have? 3. We have region of convergence less than minus 1, region of convergence between negative 1 and 2, and region of convergence greater than 2. So let's have the three possible values of h of t for these three different cases. Okay, the first case, let's say region of convergence is less than minus 1. Less than minus 1 means the overall system, h of s. But h of s depends on the two possibilities because as you see by partial fraction, s minus 1 over s plus 1 and s minus 2 is equal to a over s plus 1 plus b over s minus 2. Okay, let's find first a and b. So we break this system into two systems. That means this is one system, this is another system. To find a and b, we can do like before. We can combine this and we can crisscross a s times s minus 2 and b times s plus 1, and we equate these to the numerator polynomial. But we have another way to find a. If we see here in the denominator, we have the pole at s is equal to minus 1. So if we multiply both the left equation and the right equation by s plus 1, so if I multiply by s plus 1, what will happen? S plus 1 will cancel s plus 1 and I have a here. Here s plus 1 cancel and I will have in the left s minus 1 over s minus 2. In the right I have a plus b times s plus 1 over s minus 2. Now, if we evaluate both the left equation and the right equation at s is equal to minus 1. What is s is equal to minus 1? The pole of here for the pole for this. So evaluate at s is equal to minus 1. Here, minus 1 plus 1 is 0. So b will be eliminated. So b will be cancelled. So I will have only a. So I evaluate the left equation at s is equal to minus 1. So a is equal to s minus 1 over s minus 2 at s is equal to minus 1. At s is equal to minus 1. So let's go here. So at s is equal to minus 1, I put minus 1 here. So we will have 2 over 3. What about to get b? To get the value of b? Same. We look to the poles of B. What is the pole of B? The pole of B is S is equal to 2. At S is equal to 2, I have pole. So if I multiply both the left and the right equation by S minus 2, multiply by S minus 2, S minus 2 will cancel S minus 2. I will have here in the left S minus 1 over S plus 1. And in the right, I have A times S minus 2 over S plus 1. But this, for the B case, it is cancelled. S minus 2 cancel S minus 2 plus B. Now I can evaluate both the left equation and the right equation at S is equal to 2. When I evaluate at S is equal to 2, this will be 2 minus 2, 0. 0 times A. A will be cancelled or will be eliminated. So I will have only in the right side B. So B is basically S minus 1 over S plus 1 evaluated at S is equal to 2. At S is equal to 2. So S minus 1 over S plus 1 at S is equal to 2. Substitute 2. 2 minus 1 over 2 plus 1 is equal to 1 over 3. So this is another way to find A and B. So different way that we did before. So H of S is now 2 over 3S plus 1 plus 1 over 3 over S minus 2. Now this transfer function, it's open-ended. That means its region of convergence is not defined. So based on the 3 possible region of convergence, we will have 3 different impulse response. Okay, so let's take the first case. You see, this one has alternative less than minus 1. The first part, it has 2 alternatives: region of convergence less than minus 1 and region of convergence greater than minus 1. When the region of convergence is less than minus 1, it will be right-sided signal. When the region of convergence is greater than minus 1, it will be right-sided signal. When it is less than minus 1, it will be left-sided signal. And this one has also 2 possibilities. When the region of convergence is greater than 2, it is right-sided, and when it is less than 2, it is left-sided. Now let's take the first case. Let's the overall system. The overall system means both the region of convergence R1 and R2. They lay in real of S less than minus 1, which means R, the overall region of convergence, is equal to R1 intersection with R2. R1 means region 1 for the first part, R2 region 2 for the second part. So the intersection of the two is less than minus 1. In that case, if the intersection of the two is less than minus 1, what should be R1? R1 should be the region of convergence of R1 should be less than minus 1 to be in this region, okay, to be in the common region. So the region of convergence of R1 should be less than minus 1. What about the region of convergence of R2? R2 has 2 possibilities, greater than 2 and less than 2. But to be in the common region, what is the common region? The common region is real of S less than minus 1. To be in the common region, which option we should choose? Less than 2. Less than 2. So R1 real of S less than minus 1, R2 real of S less than 2. So in this case, both the first one is left-sided signal, the second one is left-sided. So we use the rule of left-sided signal. So the inverse of this will be minus 2 over 3 e to the power of minus t u times minus t, left-sided signal. And the second one will be also left-sided, minus 1 over 3 e to the power of 2t u minus t. Now, if we see this, is this causal system? No, of course, because u minus t. U minus t, if I have u minus t, that means h of t is different from 0 for t less than 0. Therefore, it is not causal system. Is it a stable system? No. Why? Because the region of convergence does not include the j omega axis. Remember, what is the j omega axis? The j omega axis is real of S, which is sigma, is equal to 0. But we already side here is real of s is less than -1. So it does not include. So it is not a stable system. So it is not causal system. It is unstable. It is also non-causal system, both unstable and non-causal. Now let's talk about case 2. Case 2, region of convergence between -1 and 2. So if it is between -1 and 2, what will be the impulse response? Okay, now if it is negative between -1 and 2, what should be R1? R1 has two alternatives, less than -1 and greater than -1. Therefore, which one we should choose? To be in the common region greater than -1. So we choose greater than -1. So the first region is real of s greater than -1. What about the second region? To be in this common region, it should stay less than 2. So R1 is greater than -1, R2 is less than 2. Therefore, the first system is right-sided, the first one is right-sided, and the second is left-sided. So we use the rule to change it to time domain. We use the inverse Laplace transform for the right-sided. So 2 over 3 e to the power of minus tut, and this one stays left-sided, minus 1 over 3 e to the power of 2t u minus t. Now, is this system causal? No, it's non-causal. Why? Because I still have u minus t, which makes h of t different from 0 for t less than 0. Is this system stable? Yes, it is stable. Why? Because the region of convergence is between -1 and 2, which includes the j omega axis. What is the j omega axis? Real of s, which is equal to sigma, is equal to 0. So the system is stable, but it is not causal. It is stable and non-causal. And the last option is case 3, real of s greater than 2. That means the common region for R1 and R2 is greater than 2, the common region. So what should be R1? To have an intersection with real of s greater than 2. So it should be right-sided, clear, because if real of s is less than -1, it will not be in the common region in real of s greater than 2. So the first one is right-sided. Okay, the first one is right-sided, and also the second one is also right-sided. So real of s greater than 2, I will have in both cases right-sided signal, 2 over 3 e raised to minus tut plus 1 over 3 e raised to 2tut. Is this system causal? Yes, because of ut, and h of t is equal to 0 for t less than 0. Is this system stable? No. Why? Because the region of convergence does not include the j omega axis. Remember, what's the j omega axis? Real of s is equal to sigma is equal to 0. And it doesn't include, it is not in this region, in real of s greater than 2. Therefore, it is not stable. So the system is unstable, but it is causal system. Okay, unstability, we can check it also from the time domain expression. If you see this in the time domain expression, the first part, e to the power of minus t, is decaying function, and the second one is growing because e to the power of 2t. Then we know it's a growing exponential function. H of t is a growing exponential function. The overall system will become unstable because the energy will not be finite. And if I see the second region, this one u minus t means we are going. No, the second region is this one, e to the power of minus tut. This is decaying. And what about this e to the power of 2t u minus t? Because u minus t is going to the negative, this will be decaying. So both will be decaying. Then I will have a finite integrable impulse response. So that means the system will be stable. And the first option is this one u minus t. Because of minus t, this t is going to the negative. This will be growing. This will be decaying. but overall it will be growing and it will not be stable. So by this way, we can determine the impulse response, and by looking the region of convergence, we can say the system is causal, non-causal, stable, and unstable. So that's all about today's lecture. In the next lecture, we will study about systems characterized by linear constant coefficient differential equation. Please look at the examples again in this lecture notes and in the slides. Thank you for listening to this lecture.